Right now, somewhere above your head, a rock is falling toward Earth. That happens every single day. Thousands of meteors enter our atmosphere before sunrise, burn up, and disappear without anyone noticing. Most are the size of a grain of sand. A few are larger, the size of a pebble, a basketball, a car. They glow white hot as they fall, streak across the sky for a few seconds, and then they're gone. Harmless, invisible, completely ordinary. But scientists have spent decades quietly asking a question that is anything but ordinary. What if one of those falling rocks wasn't made of normal matter? What if it was made of the one substance in the known universe that destroys whatever it touches, including the very air it passes through? What if a meteor made of antimatter hit Earth? To understand the answer, you first need to understand what antimatter actually is. Because most people picture something out of a science fiction movie, and the reality is both stranger and more grounded than that. Antimatter is real. We make it here on Earth, right now, in particle accelerators, like CERN in Switzerland. It's not exotic or theoretical, it's physics, and the universe itself produced enormous quantities of it at the very beginning, in the first fraction of a second, after the Big Bang, when the cosmos was still a hot, dense, violent place where the rules of reality were still being written. Here is the basic idea. Every particle of matter has a mirror image twin called an antiparticle. Protons have antiprotons. Electrons have positrons. These twins are nearly identical. Same mass, our same behavior, but they carry opposite charge and opposite quantum properties. And when a particle meets its antiparticle, both of them vanish instantly, completely. They convert entirely into pure energy, a burst of gamma radiation moving at the speed of light. Physicists call this process annihilation, and it is, gram for gram, the most energetic event in the known universe. More efficient than nuclear fusion, more powerful than any bomb ever built. There is no waste, no leftover material, no byproduct of any kind, just pure immediate energy. Now here's where the story gets complicated. In the early universe, matter and antimatter should have been produced in equal amounts. That's what the equations predict. But look around you. Everything you can see, every star, every planet, every atom in your body is made of matter. So the antimatter is gone. Where did it go? That question is known as the matter-antimatter asymmetry problem, and it is one of the deepest unsolved mysteries in all of physics. The leading theory is that something, some tiny imbalance baked into the laws of physics, meant that slightly more matter than antimatter was created, roughly one extra matter particle for every billion pairs. That tiny margin was enough. The matter survived. The antimatter annihilated itself into radiation. And that leftover 1 in a billion margin of matter eventually became everything you have ever seen or touched. But here is where the speculation begins. Some physicists have proposed that in the chaotic, turbulent conditions of the early universe, small, isolated pockets of antimatter might have survived. If those pockets were large enough and separated enough from surrounding matter, they could have clumped together under gravity, just like normal matter does. They could have formed structures, clouds, eventually perhaps antimatter stars, antimatter planets, and yes, antimatter meteors, drifting through space like any other rock, invisible and indistinguishable from a distance. So let's run the scenario. Imagine an antimatter meteor about the size of a car, roughly 2,000 kilograms, somehow surviving the long journey through space and entering a collision course with Earth. What happens next unfolds in a way that has no parallel in ordinary physics. As it enters the upper atmosphere, the first molecules of air it contacts, nitrogen, oxygen, touch the surface of the antimatter object, and the moment they do, they annihilate. A flash of gamma radiation erupts from the contact point. The next layer of air hits, more annihilation, more energy, then the next layer, and the next. Unlike a normal meteor, which burns from the outside in as friction heats it, an antimatter meteor would be eating the atmosphere itself. Every centimeter it travels is a continuous chain of microscopic nuclear scale explosions. The object doesn't just glow, it detonates over and over at every surface it touches, losing mass rapidly as the air destroys it from the outside in. The energy released in this process is almost impossible to hold in your mind. A car-sized antimatter meteor, fully annihilated, would release energy roughly equivalent to 85,000 megatons of TNT. To put that in perspective, the largest nuclear weapon ever detonated, the Soviet Tsar Bomba, and tested in 1961, had a yield of about 50 megatons. We are talking about an explosion more than 1,700 times more powerful. And that is the small one. The shock wave from such an event would be felt across an entire continent. The gamma radiation released would penetrate deep into the atmosphere. Cities within hundreds of kilometers of the impact zone would be obliterated, not by fire or debris, but by the raw physics of matter and antimatter ceasing to exist simultaneously. The sky itself, at the moment of annihilation, would briefly become the most energetic place on Earth. A larger antimatter meteor, the size of a building or a city block, would release energy on a scale capable of altering the global climate. The ozone layer could be catastrophically damaged. Temperatures could shift. Secondary wildfires would ignite across continents. We are not talking about a regional disaster. We are talking about a before and after moment in the history of life on this planet. And here's the thing. People have actually wondered whether something like this already happened. On the 30th of June, 1908, something exploded above a remote stretch of Siberian wilderness called Tunguska. The blast flattened more than 2,000 square kilometers of forest, an area roughly the size of a major metropolitan area. And the shockwave was recorded by instruments across Europe and Asia. But when investigators eventually made it to the site, they found no crater, no fragments, no debris of any kind. For years, the antimatter hypothesis circulated as a fringe, but not entirely dismissible explanation. Tells you if the meteor had been made of antimatter, it would have annihilated completely before reaching the ground. That would explain the missing crater. That would explain the missing fragments. It was on the surface a surprisingly clean fit, but the physics didn't hold up. An antimatter annihilation event of that scale would have produced a very specific signature. A burst of high-energy gamma rays, bright and unmistakable, recordable by any sensitive instrument of the era. No such signature was detected, and the more scientists studied the blast pattern, the heat distribution, and the eyewitness accounts, the clearer it became. Tunguska was almost certainly a comet or rocky asteroid that exploded in the air before impact. What's called an airburst. No crater needed, no antimatter required. Free. And that brings us to why scientists are not actually losing sleep over this scenario. Antimatter objects, even if they exist somewhere in the universe, face a survival problem that is essentially insurmountable. Space looks empty, but it isn't. Between the stars, there are thin clouds of hydrogen gas and microscopic dust. Just a handful of atoms per cubic centimeter. For an antimatter object, every single one of those atoms is a slow-motion death sentence. Each encounter chips away at the object, releasing a tiny burst of energy. Over millions and millions of years, the object simply erodes into radiation. For an antimatter meteor to reach Earth, it would have to travel an unimaginable distance, potentially from a region of the universe dominated by antimatter, without encountering enough matter to destroy it first. The probability of that happening and then happening to intersect with Earth's specific orbit at the right moment is so vanishingly small that it barely registers as a risk on any meaningful timescale. We also have eyes on the sky designed specifically for this. Gamma ray observatories, orbiting telescopes that scan the cosmos for the exact signature of matter-antimatter annihilation, have been running for decades. If there were significant concentrations of antimatter anywhere near our cosmic neighborhood, they would glow in gamma rays. We would see them. So far, we don't. But here's what I keep coming back to. The fact that we had to check, the fact that physicists sat down and worked through the equations, that we built satellites and pointed them at the sky, that we analyzed the Tunguska data looking for a gamma ray fingerprint. That says something. It says that the universe is strange enough and our understanding of it incomplete enough that we can't simply assume nothing unusual is out there. We have never found large-scale antimatter structures in space. But the deep asymmetry that should have produced them, the fundamental imbalance between matter and antimatter, is still not fully explained. The math that says antimatter regions can exist is not airtight, and the universe, as a general rule, does not care much about our expectations. Ordinary meteors hit Earth every day. The universe mostly sends us pebbles. But somewhere in the equations, in the unsolved corners of physics, there is a version of reality where it sends something else. And the strange, quiet work of science is making sure we'd see it coming.